Hey, okay, I can get started. I wanted to talk about the final exam, but I'm going to wait. There's usually 8 people in lecture, so I'll wait for the other 2 people to show up first. Um, so last time we were discussing circuits, and we had some elements in circuits. We had resistors. And the idea behind resistors was that the voltage drop in a resistor is the resistance times the currents, where there's some resistance R associated with this component. Then we had inductors. Which had a certain inductance associated with them. And the idea was that inductance resists changes in currents. So the voltage drop across an inductor is actually, inductance is denoted with L. The voltage drop is L times the derivative of the current with respect to time. And then we had capacitors. And there were 2 equivalent ways to formulate that. One way would be to say that there's a certain charge accumulated here, and that's the voltage drop is equal to 1 over the capacitance times the stored voltage. So this was way 1 to say it. But if we sort of have an equation that's so to write it in way beta, the change in voltage, the change in charge is exactly the currents, because the current specifies how much charge there's moving. So how much charge is accumulating is exactly the currents. But then as a result of this, or rather, I think that this equation is more general. You can say that's the change of voltage times the capacitance, where this is the voltage drop across the elements, is equal to the currents. And as it'll turn out, this equation is actually going to be a bit more useful. And this equation sort of gives a parallel between the equation for inductors and for capacitors. There's a duality between them. And then you might have things like batteries or energy sources. And sort of V is given by E, which might be a function of T. And generally, we will write some things. If the is constant. So if you have something like a battery which has a constant voltage, then you'd actually draw this like this, where sort of the positive side is the big side, I think. So by definition, sort of you take your currents to be in the direction facing positive. And so this is V is equal to E constants. And then the other case is if the power source is exactly oscillating, then you write it like this. And we could write this as maybe E sine, then some frequency. I think I wrote, it wasn't beta. What did I write last time for my frequency for my, no, omega. Omega is my, well, omega, 2 pi factor of omega is the frequency. And then delta was my constants. Right, so now you know how engineers write things. Or people who study circuits. I guess that's synonymous with electrical engineers. So, okay, we have these elements and then we have power sources, which sort of are going to give the inhomogeneous part of a differential equation. And they can either be written like a general function or a constant function or an oscillating function. And we studied a lot at the behavior of how these act with second order differential equations, with this as sort of the inputs, the forcing function. So this gives our forcing functions. Oh, okay, now we have 8 people. Good. So I can now talk about the final exam. So the semester ends on the 16th, which is a Tuesday. So I think sort of the obvious thing is that I'm going to write an assignment and I'm going to put out the third and last assignment tomorrow. No, not tomorrow, on Friday. And then it's going to be due next Friday. And then after Friday comes the weekends. And on the weekends, so before the, so there's the 16th, then there's the 15th, let's count backwards, and there's the 13th and the 14th. So the 13th and the 14th are going to be Saturday and Sunday, and I'm going to release the final exam problems on that weekend, and then you'll have the weekend to work on the problems. And then the final exam is supposed to be an oral exam, but where you've had access to the problems ahead of time. And so I'm going to create a bunch of slots that you can sign up for on Monday and Tuesday. And the oral exam will be, well, either 20 or 25 minutes. I think there's so maybe 25 minutes. So maybe I can do 30-minute time slots with 25-minute exams at 5 minutes of me looking at your paper ahead of that. So does that sound good to everyone?
It will be an exam you could do in like 1 day, not 2 days, right?
Sorry, say that again. My volume was pretty low.
It will be like you won't have to use both days, right?
I think that the exam that I set for the midterm was a bit long. So it's not going to be longer than the midterm. I think there was just a lot of like linear systems and they take a very long time. I'll put fewer linear systems on it. But it won't be like, if the midterm took 2 days, then it won't be half that length. It'll be a bit shorter than the midterm is the answer. And then everyone will have the same submission deadline. So just because you're doing an exam on Tuesday doesn't mean you get to like submit later. So probably I'm going to start exams like on noon on Monday. And then noon on Monday is probably going to be the submission deadline. I don't have to release it at noon on Saturday. I can release it at midnight on Friday. That also works. Right. Any other questions? I'll send an email with this soon. Right. So last time we analyzed a circuit that basically looked like this. So we had an energy source, and then we had all 3 of these elements hooked up in series. And this gave rise to a second order differential equation. Okay. So I set this up last time, but I'm going to do it a bit differently this time. Now I'm going to set this up as a 2x2 system instead of a second order differential equation. So there's E, there's R, there's C, and there's L, and then there's a current here, I. And the catch is that basically what we're going to do is we're going to say that there's an unknown voltage drop across here. Instead of representing the charge, it's actually better to represent V as the voltage drop across this instead of giving it in terms of charge. So if we're setting up as a second order system, which is going to be equivalent to the equation that we got before, then the equations that we'll have is by Kirchhoff's voltage law, E, sort of the energy being inputted into the system, has to equal the voltage drops across all of these components. And if current is in this way, it's RI, then V is going to be the unknown voltage drop across the capacitor. And then we're going to have L, where the voltage drop here is L di dt. So keeping this as a state variable V is good for being able to give it as like a first order linear system. And then the second equation is, I guess, the equation that connects V. So we know that also V, or rather dV dt times the capacitance is equal to I. Now, this basically already isolates everything. So what we're going to do is, let's say I is the first one and V is the second one. So what we have then, this is an inefficient use of space. Maybe I also want this to be a bit away from this equation, and these aren't aligned. Okay, so what I'm going to get as a result is that di dt is equal to, so I is the first one, so it's negative R over L I. And then it's negative 1 over L V. And then there's the inhomogeneous term, 1 over L E. And it's going to be a common pattern in these equations because the derivatives have something associated with them that's not a reciprocal. That's when you divide through, you're going to get reciprocals on everything else. And then the second equation is that dV dt is equal to, so just 1 over Ci. And this is now a second order system, inhomogeneous second order, inhomogeneous first order linear system of size 2, which is different, which is equivalent to rather the second order just differential equation that we got last time. If you sort of substitute it in, you'll get the same differential equation. Okay, so let's do something slightly more interesting. Let's suppose now that we have, and I'm really going to care more about setting these up than solving them, because solving them might depend on the specific numbers in question. For example, sometimes you'll have real and sometimes you'll have complex eigenvalues, and that really depends on what exactly the numbers are. On the homework, I'll put some questions of numbers, but you already know how to solve the equations, so. And then we're going to add a state variable V for the voltage drop across here. And then we're going to have 3 currents, one in this block, one in this block, and one in this block. Now we have Kirchhoff's, which I'm going to have to look up how to spell.
Is there a voltage source?
No, there isn't. Not in this example. So it's going to be a homogeneous differential equation. So for example, you can imagine in real life, let's suppose that you have a charged dangerous capacitor that you've just removed. So you've charged the capacitor in some circuit, then you remove it. It's still going to have the charge discrepancy stored between the plates. Then you add it to this system. And then at time 0, you sort of have no current anywhere. But you have this voltage drop, and then you can let it go from there. So you've just connected, and then the current builds up. And the current is going to sort of build up continuously because this thing resists current buildup. Right, where is, how do I spell Kirchhoff? Yes, so we have her CHH. So current law. And that's currents going in and out of a node sum to 0. So conservation of currents. So current going in is current going out, because otherwise charge would be building up, and it's not going to be the case apart from a capacitor locally, but globally the charge in a capacitor is so for example, if it happens that a capacitor didn't build up as much positive charge on one plate as negative charge on another plate, then the capacitor would get a net charge. And then you could imagine Kirchhoff's current law being violated. But sort of the fact that within each component, the fact that they remain electrically neutral and conservation of charge means that the current coming in is going out, because there isn't like a net charge building up on anything. So sum of currents going in is the sum of currents going out. Okay, that is in fact how you spell going. Interesting. So apart from the voltage law, this is going to let us set up interesting systems. So here there are sort of two nodes. I can sort of denote them here and here. And in general, if you sort of have one line connecting two nodes, the currents there is going to be the same everywhere, because again, charge isn't somehow building up on some elements. Net charge at least. So what we have is that at this node, we're going to have the equation that all of these are outgoing things, and there are no ingoing things. So I1 plus I2 plus I3, the outgoing currents, is equal to the incoming currents, which there are none. So we have this. And at this equation, we have just on the right-hand side, all of the three currents are incoming. So we get the same equation for this node. Both equations give the same node. Both nodes give the same equation, rather. Cool. So then what's going to happen is that we have two circuits. We have this loop here and this loop here. And we can do an analysis along the voltage drops on a loop. Now, how it actually works is that we're not going to care about the direction of the loop. So maybe I shouldn't draw it as sort of directed things. So here is one loop, and here is a second loop. Um, Actually, I may have made a mistake when I set these equations up. I think we do actually want to give this a direction, and I think that there might actually be minus signs that I didn't account for. Let me just quickly look at the source material for a second. Actually, I could look at this book as well. So yeah, exactly. Okay. Yeah. So I have sign errors everywhere. That's unfortunate. So basically what we're going to do for analyzing this is we are going to actually give this loop a direction. And what happens is when the current is flowing in this direction, there's going to be a voltage drop in this way. But when the current is flowing in the opposite direction, the voltage drop is actually going to happen this way, which is against the direction that we set, right? So we're going to get a negative sign here. So what's actually going to happen is that here, sort of, if we've chosen to orient this in this direction, then as we go along, this is a positive voltage drop. So it's going to be V. And then as we go across here, this is going to be minus RI2. And the current here is I2, so that's why it's RI2. Now here, so that's equal to 0 because there's no energy inputs into the system. And here what we have, I should also align this equation with this one. That's not a good 0. I could draw a better 0. And on this one, then, what we have is that's positive RI2. And then we're going to go here, it's going to be negative. So what's the voltage drop across a inductor? Well, it's di dt. And so that's I3. And what we also have is just the definition here of the state variable V. And that's going to be that C dV dt equals I1. Okay, so how this game works is that there are two things that have differentials on them. And then there are 4 variables, but there are also 4 equations. And we can use these 2 equations that don't have derivatives to get rid of 2 of the variables. And so what variables are we going to want to leave this equation of? If we're choosing 2 variables to actually leave it in terms of what would those variables be?
In RL and C?
No, RL and C are constants. The 4 variables that change with time. Sorry. Yeah. So the 4 sort of dependent time. The 4 functions of time are these things, right? The 3 currents and the voltage drop across the capacitor. So we're going to eliminate 2 of those 4 things using these 2 equations.
Well, you could get like I3 in terms of I. Oh, well, maybe you oh yeah, you would get I3 in terms of I1 and I2 and V in terms of I2.
But we just want two equations in terms of just two variables so that we can solve that system. So we're going to use these two equations to completely get rid of two of these variables. So the question is, which ones stay? And there's a really good reason for choosing a specific ones to stay. So the answer is that we're differentiating these things here, and we'd like to have a first order system. And so we don't want to mix multiple derivatives in an equation. For example, if we try to get rid of I3, then we'd have two derivatives in the same equation, and then we can't rearrange that to be a first order system in the usual way. I mean, we basically have to undo what we did in order to do that. So we're going to keep it in terms of I3 and V because those are the things that the derivatives are on. And then you sort of can't get rid of three variables using three equations because actually there are derivatives. So the derivatives are the things that are preventing us from just solving four equations with four unknowns, because you actually have to do the differential equation step there. Because there are derivatives on I3 and V, and as we have two equations with no derivatives. We will pass to a 2x2 system in only I3 and V. And you can imagine cases where you sort of already have multiple derivatives in a single loop because I put two inductors in that loop, and that's annoying. And you have to do a bit of algebra to make it into a system that you know how to solve. There are more general methods for solving systems that sort of have mixed things. But I'm not going to give you the annoying cases where there are two inductors in the same loop. You're always going to be able to set it up where sort of the inductors and the capacitors are the things that, well, actually, no. The capacitors, you can have capacitors and inductors in the same loop. Capacitors introduce their own differential equation for this new voltage variable. But having two inductors would be bad, as then you'd be mixing derivatives. And then you'd have to unmix them later. So this technique is like not 100% fully general because you have to do some ad hoc things in other cases. And what this is called is it's called the state variable approach to circuit analysis. And the state variable is adding this. So this is the state. And the benefit of the state variable approach is that sort of the alternative is what we did last time, which is to get rid of V entirely and to just differentiate these equations that sort of have charge involved, so that everything becomes a second order differential equation. But then you'll have a second order system, not a first order system. And I mean, you can solve that with a Laplace transform, no problem, right? We saw that Laplace transforms can do arbitrary linear systems, no problem. But if you're trying to solve it using the matrix linear algebra approach, then it's not going to be so easy if you have a second order system. But the state variable approach, which introduces these new state variables and new differential equations, lets you get things in terms of a first order system. So that's the main benefits here. That's why we introduce a new state variable v. So looking at these equations then, what we're going to do is we're going to manipulate them. So we want to get rid of I1 and I2 entirely. So how do you do that? Okay, so we are going to get that C dv dt. I1 is not one of the variables that we want. So we're going to use this equation to make it minus I2 minus I3, right? So we got rid of I1, but we still have I2. Well, how can I rewrite this? Sort of minus I2. We can use this equation to eliminate it. So we get that it's minus V over R. And the signs in my notes are wrong, so sad. But it's going to be minus 1 over R V, because that's what I2 is equal to. Rather, that's what minus I2 is equal to. And then we're going to get minus I3 as before. So good. We've managed to eliminate I1 and I2 from this equation. Maybe I can, I guess, write the chain of reasoning a bit more explicitly and write, well, this is equal to I1. And then maybe I can number my equations. Let's call this equation alpha, beta, gamma, delta. So we start off with equation delta. Then we use equation alpha. Then we use equation beta as sort of the justification. You don't have to do this, but this is a bit helpful in just seeing what's going on. Cool. So now the other equation that has a derivative is this one. So we have that's L times di3 dt. Is equal to, so it's positive Ri2. And that's by equation gamma. Now, I2 is not the state variable that we want, but we already have Ri2 here. Ri2 is equal to V, right? By equation beta. But look, this is V in terms of V and I3 in terms of V and I3. So overall, we then get that sort of V prime, I3 prime is equal to, so V is first, so I'm going to have negative 1 over RC. Now, I sure would love to be an undergrad again and have like ENM fresh in my head. I took the full ENM sequence, but like I don't remember, so I can't do things like what's it called? Dimension analysis to actually check that these expressions make sense, because we sort of have that the derivative of voltage is equal to 1 over RC times, so the input here is going to be a another voltage. And then does that actually have units of volts per second, which would be the time derivative of that. So I really can't check my equation, but if you'd be sort of like a person who's minded in actually remembering this stuff, then you'd be able to sort of sanity check your equations by just checking whether they're dimensionally correct, which is sort of like this super big shortcuts, massive trick that people in physics have to ensure that they don't write wrong equations. It's sort of amazing. Anyway, so -1 over RC, and then -1 over just C. And then here you have sort of V is first, so that's the first equation. So it's going to be 1 over L. And this is not aligned. That is a lot more aligned, although it's slightly bigger. And so this, because there's no voltage source, as you mentioned, is going to be a homogeneous equation. And then once you know V and I3, you can solve for the other variables just using this. So this is a familiar first order linear homogeneous system. Yay. Good. So again, basically you can sort of have arbitrary numbers here if you set them, except there's going to be a 0 here, which means that you can sort of get all of the types of behaviors of second order, sorry, 2x2 first order systems with constant coefficients that we studied. I guess I can add first order linear constant coefficients. It's even better. Okay, let's do another example. Any questions about this one? Cool. So example 2. Oh, I see. I was missing such a break between these two equations. I moved stuff down, but oh, I guess it's not as nice as I would have wanted. So suppose that you have, in this case, we're actually going to have a voltage source. And then suppose you have an inductor here. And then suppose you have a capacitor here. And then suppose you have another inductor here. And then suppose you have a resistor here. Okay. Yeah, that's good. So we're going to introduce 3 currents on here. I1, I2, and I3. And then this is going to have some inductance L1. This is going to have some inductance L2. This will have some capacitance C, and this will have some resistance R. Okay, that looks good. So the other thing is that we're going to introduce a state variable V for this capacitor. And also, I guess I don't like this line because it's not the same length as that one. Except I need to change my pen color back to red. Because otherwise it looks like a battery if they're not the same line. Actually, the book that I'm using draws capacitors like this. So maybe I'm making a mistake, but the other book, yeah, it also draws capacitors like this. So capacitors are actually probably drawn like this and not like this. But that's a minor point. So if we're setting up the equations, then sort of we have 2 nodes. And the equations that we get from Kirchhoff's laws are the same at both of these nodes. So from Kirchhoff's law, we get I1, which is the inputs here, is equal to the outputs, which is I2 plus I3. Then we're going to give these loops an orientation. And look, all of this is positively oriented on this loop. Whereas on this loop, some terms are going to cancel out. I mean, not cancel out, but this current opposes this. So then using Kirchhoff's voltage law, we have that E is equal to, so then there's going to be this, which is going to be positive. So it's going to be L di1 dt. And then this is also positive, given this orientation, plus V. And then on this loop, what we're going to have is, and I actually do want to align these equations, 0 is equal to, then we're going to have L2. Oh, so this is L1. The L's are numbered. L2 di3 dt. Then we're going to have plus Ri3. And then we're going to have minus V, because this air loop goes the opposite direction of this. And then finally, we have one more equation, which is the state equation for this, which says that C dV dt is equal to I2. So there are 3 equations that have derivatives in them. And then there are 4 variables, and we have another equation to bring it down to a 3x3 system. So this is how state variable analysis is always going to work. So let's say the order is going to be I1, I3, and V. We want to get rid of I2. Well, getting rid of I2 is sort of easy because this doesn't involve I2, this doesn't involve I2. But this involves I2, but we can just rewrite it in terms of I1 minus I3, right? So overall, we get di1 dt is equal to negative 1 over L1 V plus 1 over L1 E. And then maybe I can write that this is a function of time to show that it's the inhomogeneous part. Then for I3, we're going to get, so I3 is the first one. So it's going to be minus R over L2. I3. And then minus, or rather plus 1 over L2 times B. And then finally, we're going to get that dV dt is equal to so I2 is I1 minus I3. 1 over C I1 minus 1 over C I3. So I2 is I1 minus I3. Good. So as a result, we get that I1 prime, I3 prime, V prime. So I'm going to write the matrix bars here, but first I'm going to fill in maybe, okay, no, fine, I can do. Then here, so it's I1, I3, V. So I1, I3 are 0 here. I want an inhomogeneous part. Nope. The opposites of undo. Okay, then on the second row, it's I1, I3, V. Then it's I1, I3. I guess I've been writing them as slant fractions. And V. But there's also an inhomogeneous part. Which is 1 over L1, so E of T over L1. And again, the specific solution to this depends on the numbers, because you get different behavior. Okay, but good, cool. We set up that system. So those are the examples that I have of this. I could do some more elaborate examples, but on the homework, you just do this, and the stated variable analysis method that I explained is going to work. So now we're actually going to do some dynamics and prove theorems about motion. So this is more on the end of physics that you'd see in a physics course, but we're going to do it with differential equations. Although it's already 51, so now it's a good time to take a break. So let's resume at 7:05. See you then. Oh, and before I move on to dynamics, I do actually want to mention one thing. So we saw this circuit here, and the book actually explains what the circuit does. So if you look at the book, then they consider the circuits. And by the way, this book is not good for most of the things that we're doing. It's just good for some of the applications. Like I've used at least 4 sources now in a very major way. That is a true statement, yes. So what they do is they consider some specific values for what L1, L2, C, and R are, and then they consider having an input which is sinusoidal. And then they consider 2 different frequencies. And you can see that sort of the steady state solution. So there's going to be inhomogeneous solutions, and those are probably going to decay exponentially given the numbers. They usually decay exponentially. But what's the steady state solution, which is what we're interested in, it looks like this. So the blue curve is going to be your input curve. And the black curve is going to be your steady state output curve. So you can see that, for example, for omega equals 1/2, the steady state output is basically at the same amplitude as the steady state inputs. Whereas if you increase the amplitude of if you increase the frequency of the inputs, then the outputs gets greatly attenuated. I guess this isn't the steady state output because this is, you can see sort of this peak is bigger than this one. So this is perhaps the full solution, although the steady state solution sort of emerges after a while, right? And so what they call it here is a low pass filter. So given input signals, it selects for the frequencies in the input signal. If it's, for example, a sum of frequencies, then by linearity, you'd have a sum of outputs. And so if you imagine sort of taking the Fourier transform of your input, which is decomposing it into a bunch of frequencies, decomposing it into a bunch of sine waves, then what's going to happen is that for low frequencies, those are going to be preserved, but for high frequencies, they're going to get squashed. And so this is a way of sort of, if you have an input for selecting for the low frequencies. And you can also construct a high pass filter like this. And so I imagine that if you have something like a radio and you're tuning the radio, then what you're doing is using circuits analogous to this to select for certain frequencies. I guess AM and FM would work slightly differently. But anyway, so this actually has a really cool application. And if any of you are remotely adjacent to electrical engineering, this probably sounds really exciting. It does to me as well. Okay, so physics time. And I have no notes, so time to just okay, so first off, we need a sort of a preamble about radial coordinates. Rather, let's say vector analysis preamble. And this is going to be the planar case. So in general, what's going to happen is that you're going to have some position, which is going to be a vector. Let's say it lives in the plane. So you're going to have some sort of, I guess, position. Then you're going to have some sort of velocity and some sort of acceleration. And these things are related by derivatives. So in particular, as vector valued functions, at the moment, it's not specific to the plane. S prime is equal to V, and V prime is equal to A. And sort of the governing thing is that if you have some sort of body, which might be represented as being located at some position, if it's sort of compound, then that position is going to be its center of mass. Then what you can imagine is that there's some force that's acting on the object. And the force is going to be a vector that's sort of rooted at that point. So Newton's second law says force is equal to mass times acceleration, and the acceleration is in the direction of the force. And you can sort of think of this as sort of being a definition of what force is, operatively. It does say more than that, of course. For example, it says that if you have multiple forces acting on an object, then the accelerations are going to be proportional to the sum of those forces. Now, what's going to happen is that suppose that we sort of have a plane, and we have some origin, which I can denote by O. And sort of we get to choose what the origin is arbitrarily, and we're going to choose it such that the coordinates are nice. And then suppose you have some point here. And this is going to be your point, maybe S. And so we can imagine sort of a line connecting these two. Then what S is as a vector, if this is going to be the XY plane, then what we have is basically an X coordinate and Y coordinates. So let's call this X, let's call this Y. So S is equal to XY in the plane. And this is called rectangular coordinates. Now, the deal is that there's another way to represent this. Let's suppose that you sort of have an angle instead and a radius. Then you can also represent S as being the pair R theta. And this is called polar coordinates. But for polar coordinates, something interesting is going to happen. Do I just jump there directly? I guess another thing that happens is if we sort of have a force acting on this object. Now imagine that there's basically a force acting on this object. And imagine that there's also a force acting on this object as well. So how it's going to work is that basically the force is going to have X and Y components. We can say F, for example, X is going to equal the X components of the force. So if we sort of imagine that in the first picture, maybe I should just divide these. So in this model, let's introduce basically another angle here. And suppose this is at angle theta to sort of an imaginary x-axis anchored at this point. Then you have fx, which is going to equal sort of the magnitude of f, which is you could consider as a vector quantity. But if I don't write the vector quantity, then I'm going to just implicitly denote the magnitude times cosine of theta. And then Fy could be interpreted as the magnitude of F times sine theta. But there's other ways to interpret this. Well, F is equal to, in this case, this is the X components of force. So this would also equal M times the X component of acceleration. And this would equal the Y component of acceleration. Which we could write as, by the definition of what this is, M times the X components in general, prime prime. Okay, cool. Now for polar coordinates, we're going to do something a bit different. What's going to happen is that there's sort of a natural frame of reference for polar coordinates. And that's that if you have a vector acting on something that's located at this polar range, then what we're going to do is we're basically going to extend this vector. And then we are going to sort of decompose this in terms of these two sides. So these components would be called the radial components of the force, FR, and the angular components of the force, which is F theta. Maybe I don't know what color should I move them in. This component right here would be FR, and this component right here would be F theta. And so what we're going to work out is what Newton's equations are in terms of polar coordinates, because that's actually something that's not trivial. So in terms of polar coordinates, we have that sort of the x coordinates is equal to r cos theta, right? And the y coordinates is equal to r sine theta. So as a result of this, we get that x prime is equal to r prime cosine theta. I usually write brackets, but I haven't written brackets. You know what? I'm not going to write brackets. Then the derivative of cosine is sine. So minus r sine theta prime. Okay, this is where brackets come in handy. Cool. And y prime is equal to r prime sine theta minus plus r cos theta times theta prime. And if you sort of think of this as a matrix in terms of sines and cosines, and the coefficients are cos theta, r sine theta, r cos theta. So that's an interesting observation to make. But then we are going to do this, and we're going to take the next derivative, and this isn't going to look nice. So x prime prime is equal to r prime prime cosine theta plus now if we take the derivative of cosine, it's going to be negative sine. And then we're going to get another theta prime by chain rule. Then here, if we take the derivative of r, we're going to get minus r prime sine theta, theta prime. And then here, well, there are two terms that have theta. Oh no, there are two terms that have theta. This is not fun. So if I took cosine theta, then this, but here, if I took derivative of r, and then I have two terms. So I'm right so far. So if we take the derivative of sine theta, we're going to get minus r cos theta times theta prime squared. And then we're going to get one more term. No room for these implication arrows. And the other term is if we differentiate this theta prime, so it's going to be minus r sine theta, theta prime prime. And so we can rewrite that as just r prime prime. What way do I want to group it? Okay, let's group it like this. Cosine theta, let's keep the derivatives at the back. Minus 2 sine theta r prime theta prime minus r cos theta theta prime squared. Let's write it a bit nicer. And then minus r sine theta theta prime prime. And y prime is also not going to be nice. You know what? Let me just write down the answer. It's going to be basically some sign slip. So it's going to be sine theta r prime prime plus 2 cosine theta r prime theta prime, and minus r sine theta theta prime squared. I remember seeing these formulas in ENM. If you look, sort of, Griffiths has both famous quantum and ENM books, and in Griffiths, these formulas are given. Sorry, this should be cosine theta plus r cosine theta. Theta prime prime. Okay, but what we're going to do is, for the moment, suppose sort of theta is equal to 0 for a second. Then r is equal to x, right? Because if theta is equal to 0, then r is just the x coordinate. R is always going to be greater than or equal to 0. Although I'm not sure that's that important. So what's going to happen at this angle, at theta is equal to 0, and then we're going to generalize. So what's going to happen is that the first two equations, we are going to plug in theta is equal to 0, so the cosines are going to survive. So what we're going to get is that x prime, and how are we going to think of x prime? We're going to think of x prime as sort of, we're going to take the velocity vector, and this would consist of the radial components of the velocity vector. So this is used from this equation, is equal to r prime, which we're going to use as dx dt. And sort of the oh, right. So r d theta dt is going to equal r theta prime is going to equal v y. Rather v theta. And the reason is that sort of how quickly your angle is changing, how quickly you're moving up, it's proportional to the radius, right? So then we're going to see that v theta is equal to, so this is going to become 1, and this is going to be our theta prime, so that's v theta. So that's equal to y prime. Then how these next two equations are going to change is that x prime prime. Oh, okay. Rather, I sort of did this backwards. What this equation gives is that x prime. So let's give these equations numbers. So one gives x prime, so at theta is equal to 0, is equal to r prime, which is also known as v r. Equation 2 gives y prime is equal to r theta prime, which is also known as v theta. Equation 3 gives x prime prime is equal to, so the cosine terms survive, r prime prime minus r theta prime squared. Oh, okay. Right. Okay. Rather than thinking about what's these equations become, this is sort of simpler. Sort of just in general, because the coordinate systems align. What we have is that VR is equal to x prime. V theta is equal to y prime. And then acceleration in the radial components is x prime prime. And acceleration in the theta components is y prime prime. So then we ask what the equations give. Then equation 1 just says that VR is equal to, this is the theta is equal to 0 case. R prime. Equation 2. So there we actually derive equation 2 from this, which is different from what I said before, in which I just gave it. Says that the theta is equal to r theta prime. Equation 3 says now that if we look at x prime prime, which is equal to AR, then that's equal to, so we're going to get r prime prime. Then we're going to get minus r cos theta. No, minus r cos theta is 1. Theta prime squared. And equation 4 is going to give that a theta is equal to so now this term survives. So 2r prime theta prime. And then plus r theta prime prime. Now, here's going to be this ridiculously clever swindle that we're going to do. And that's that, notice that these equations do not make reference to x and y. So in fact, they are globally valid for all values of theta. Why? Because you can just set the x-axis and y-axis to align with whatever you're working with. So by changing coordinates, we get this for all systems. By rotating your rectangular coordinates. Get that these equations are valid for r and theta. So not just theta is equal to 0. And that's really cool. So basically what happens is that in rectangular coordinates, we sort of had a very simple equation. If we took x prime, then that was the velocity. And if we took the velocity prime, then that was the acceleration. So these equations are only valid in rectangular coordinates. On the other hand, if you're working in polar coordinates and you want to decompose into radial and angular components, which are going to look like this, then you actually have different equations. Then it's not the case that, for example, theta prime is equal to the velocity, because you have to multiply by r. Because if theta is changing at a certain rate, then if you're further along, then your velocity in this direction is quicker. So that explains this equation. But then these two equations, we actually needed to go through that derivation in order to get them. These are actually interesting equations. They say that the acceleration in the r direction is proportional to the change in the r direction, but it's also proportional to r theta prime squared. So that's curious. I mean, this is a factor. And then similarly here, you get this. So can we interpret that? So suppose that your theta is changing at a certain rate. Then how is sort of your x projection changing, which it's sort of getting shifted as well? Does anyone have a good interpretation for this term?
Oh, it's like oh, it's just like from the it's like rw squared, and then w squared equals v squared over r squared. So then it's v squared over r. So that's just oh. Mm-hmm.
So if you've seen physics formulas for sort of rotating bodies, these do come up. They are relevant. So I don't know them off the top of my head, but that sounds like it's approaching the right direction. Any more thoughts or? So it's interesting. So if we just look at sort of the radial component of acceleration, that it involves the change of angle. And that's a bit surprising because here you sort of have both of these, but then this one is also being multiplied by r prime by r prime. So that's really interesting. But anyway, so these are cool. These are formulas that are going to be relevant for the analysis that follows when we move into polar coordinates.
Wait, just to ask the question, wouldn't the acceleration, the radial acceleration, just be r prime, or what's prime?
Except it's not. We've discovered that theta prime also comes into it.
But like, what? So what does r prime mean?
So what happens is that, let's think about what the meaning is. So R is going to be, so imagine in polar coordinates that you have some velocity and you have some acceleration, right? Let's sort of imagine the case where we have centripetal motion. Maybe that'll help. So the object is moving, let's say it's moving in a circle. And what's going to happen is that sort of, you have a force acting in this direction, and your velocity is in this direction, right? So the force is going to be entirely, and the force is going to be proportional to the acceleration. Now we can sort of imagine that it's not entirely a centripetal force, but there's also another components to it. So, I mean, you ask a good question. Why isn't AR just R prime prime? And that's sort of, if you interpret all of these things correctly, it should fall out from it. So let's not call this the force because that uses Newton's law. Let's just call this the acceleration vector. So the acceleration vector will have a radial components. And by definition, that means that we take the acceleration vector and we decompose it like we did here, right? So this is the definition of the theta and r factors of the radial component, right? So then let's think about it. Suppose that you're moving with some velocity here. Oh, that's cool. Yeah, that's cool. So if you're moving in a circle, let's imagine that the force is exactly such that you move in a circle, right? Then what's going to happen, sort of, is that r prime prime is equal to 0, right? Because your radius is equal to c. So radius is equal to c in this example.
Oh, I see now.
Yes, exactly. But the fact is that there is radial acceleration because the acceleration is in fact entirely radial. So you can figure out what the radial acceleration is from this components. There we go. So isn't that cool? Okay. So I'm just going to do something completely impromptu, and I'm going to open Griffiths. I have it in my random text folder because it's a book that I consulted often in undergrads. It's not alphabetical. 1 second. Okay. Okay, I'm going to look up how to spell Griffiths, and then I'm going to yes. So if I just do, you're not seeing what I'm doing right now, but yeah, Griffiths ENM is indeed in my random text folder. I could have just done it alphabetically. So here is Griffiths. This is, if you do ENM, you will be probably studying it from this book. That's the classic undergrad ENM book. And I guess maybe at the end they have tables, or maybe at the beginning they have tables. Well, anyway, somewhere here there are tables. Are they at the ends? Yes. So here are all of the equations that you get very used to when using in ENM. So you would have well, cylindrical coordinates are even worse than radial coordinates. Now, the equations are going to involve, well, let's see the equations that sort of have a theta squared. Some of these equations will probably have a squared. Oh, but it's in terms of x and y. But spherical coordinates. Okay. Is that? I guess here they're using a slightly different coordinate system. The way that I'm doing it, it's slightly different from this. Anyway, let's get back to that. Okay, so cool. We did actually give an interpretation using the centripetal movement example for why the radial acceleration is in fact not equal to the second derivative of the radial component. So that's cool. Okay, let's, what time is it? 46? Actually do some physics now, instead of just coordinate analysis. So I called that section 1, vector analysis preamble. Okay, so 2. Plane motion. So this is going to be central forces. And so first, what we're going to begin with yeah, here we are, is what's going to happen is there's going to be an object. At first, it's going to be moving in 3D. Imagine in R3, that's there is some attracting objects. At the origin. This means that's if you're located at let's say S, the force acting on you is so we want to normalize S because if S sort of is very far away, then that shouldn't change the force factor. So it's going to be there's going to be some magnitude F of S. So F is going to be a scalar function of S. So at every point we have a force that depends on the point. And it's going to act in negative the direction of S divided by the magnitude of S. So this means that's there is a pull of magnitude Fs directed to the origin. And do I actually want to say it's sort of like negative Fs? I think in this analysis, they actually do not make it negative. Let's make it this. Let's remove the negative sign. There is a push of magnitude f as directed away from the origin. So for example, if there's a positively charged particle and you're a negatively charged particle, then there's going to be a push. But usually if it's something like gravitation, then it's an attraction, so F is going to be negative. For like we can do examples. So you can sort of have a this is your origin and there's a positive charge here, and then you are a negative charge. And so the force that's acting on you is impulsive force pointing away from the origin, right? Or you can imagine that sort of you have some mass here, and then you have some other mass here. And the gravitational attraction is going to be pulling you towards the origin. So this would be a negative F and this would be a positive F. So electric repulsion and gravitational attraction. I'm now going to prove some theorems about this scenario. I'm going to call them theorems. Theorem 1. In the case of central forces, the movement of an object is confined to a plane. To a plane through the origin. That passes through the origin. So in general, basically, if I have 3 coordinate axes, let's say this is my x-axis, this is my y-axis, and this is my z-axis. This satisfies the right-hand rule, the way that I've drawn it. And then suppose that you sort of have some force here. And it's some vector. And it's sort of hard to picture exactly where this is because there are lots of 2D projections that would have this. Anyway, suppose that you have a force, rather suppose that you're located here. And let's say that this has this X projection, this Y projection, and this Z projection. And what's going to happen when you're located there is that there's going to be an attracting force towards the origin, right? Or away from the origin. then what's going to happen is that, so this is central. We can ask sort of what the X, Y, and Z components of this are. Well, let's suppose that you're basically at some radius R. Then what's the so M X prime prime is going to equal the force, the magnitude of the force. And then there's the question of, well, how much of the force is actually pointed in the X direction? And it's going to be cosine alpha, where alpha is the angle between both of these. But another way to represent it is that sort of if you imagine a plane going through here, and this is the angle theta, then cosine is defined as the ratio of this to the hypotenuse, right? So it's actually going to be f of x over r. M y prime prime is going to be f, which is a function of x, y, and z, times y over r. And mz prime prime is equal to f times z over r. And what we're going to do is we are going to multiply these equations by stuff. So let's call these equations 1, 2, and 3. So if we consider minus y times 1 plus x times 2, then what we get is that so m x y prime prime minus m y x prime prime is equal to 0. And similarly, we can obtain other equations similarly. So at this point, I'm just going to cancel m, and I'm going to get x y prime prime minus y x prime prime is equal to 0. And so similarly, I'm going to get that y z prime prime minus z y prime prime and z x prime prime minus x z prime prime is equal to 0. Now, here's the cool thing. This is sort of some elite hacks that we have right here. If we have the integral of x y prime prime minus y x prime prime, this is with respect to time. Then what we can do is we can use integration by parts twice. So we are going to basically integrate this term and differentiate this term. So we're going to get x y prime minus y prime y x prime minus the integral of x. So integration by parts lets us move a derivative over from y to x. So x prime y prime minus y prime x prime dt. But this is 0, right? So what we get as a result is that this integral is equal to some constant. So that implies that x y prime minus y x prime is equal to some constant C1. That depends on the specific problem, the specific configuration. And similarly, we get that y z prime minus zy prime is equal to some constant C2, and that x, or rather zx prime minus x z prime is equal to some constant C3. Now what we're going to do is we are going to consider the expression C1x, or rather, actually, C1z. Yes, so what's missing here? Z is missing here. You know what? I'm going to give these constants different names. So which expression is missing x? This expression is missing x. I'll call this 1. This expression is missing y. I'll call this 2. And this expression is missing z. So I'll call this 3. So now let's consider the expression C1x plus C2y plus C2z. So what that's equal to is, well, we can write it out. X, y, z prime minus x, z, y prime. Then C2 plus y, z, x prime minus y, x, z prime, then plus. I'm starting to lose my voice. Okay, this might actually be bad. Zx y prime minus zy x prime. I'm going to finish this example and then I'm going to end the lecture. I don't think I can talk anymore. So if we look at the terms that have y prime, then you'll notice they have opposite signs, right? And if you look at the terms with x prime, you'll notice that they have opposite signs. And then if you look at the terms of z prime, you'll notice that these have opposite signs. So this is 0. So what does that say? That says that there are some constants C1, C2, C3, such that basically the dot products in vector notation with x, y, z is equal to 0. So that says that x, y, z live orthogonal to a vector. But if you sort of imagine the plane, and then you have some vector C1, C2, C3. So let's call this your C vector. Then if you consider all vectors orthogonal to this, what it'll form is a plane orthogonal to C. So this is exactly the equation of a plane for the origin. And that finishes the proof of the theorem. Okay, I actually can't talk anymore. I can't, I think I can't go louder than this at all, at the moment. So unfortunately, I'm going to have to end that here, but we're going to do a few more of these theorems next time. The next theorem is going to be conservation of angular momentum. And then the theorem after that is going to prove that if you sort of you sweep out equal areas in equal time, which is one of Kepler's laws. But the surprising thing is that that doesn't actually at all involve the fact that gravity is an inverse square law. The law about sweeping out equal areas in equal times holds for any possible central force. And I didn't know that until today. I thought it was just 1 over r squared. But it's actually any central force. Okay, so I will send you these things and I'll write something about the final exam. And I will see you tomorrow. Hopefully my voice is feeling a bit better then. Okay. Any questions? Anyway, have a nice day. Bye.